This lesson deals with looking at percent yield and percent error. So now that we are able to predict, for example, the mass of products that we get from a chemical reaction, we can now calculate the percent yield, which is basically how much of the expected product was obtained from a reaction in the lab. And so to calculate that, you can see that percent yield is the actual yield, so what you got in the lab, over the predicted yield, so what we expected from carrying out some stoichiometry. And again, it's a percent, so we multiply that by 100. Now, for high school in the labs that we do, you're going to see that our percent yield is relatively high. We have expectations of getting pretty high numbers. Not all reactions will get you 100% of the products that you want. And in particular, as you know, most reactions have spectator species that are not part in the reaction. And so if you've got to purify them out in some way, purify the product that you make, what ends up happening is that a lot of times you lose some of the product that you expect. So there are some reactions where it's completely acceptable to get percent yields that are lower than 90% because of the purification that needs to happen for that substance. So without further ado, let's actually do some questions where we're calculating the percent yield. So our first example says, a student mixes a solution that contains 4 grams of sodium hydroxide with a solution containing calcium nitrate, and a precipitate forms. The student collects and weighs the precipitate and obtains, and this is where we have to do a correction. This mass will not work. This has to be 3 grams. And it says, what is the theoretical yield? All right. So for this, it's going to be stoichiometry. So remember the 4 steps of stoichiometry. The first one is a balanced equation. And so we are going to be mixing sodium hydroxide with a solution containing calcium nitrate. And this is going to be a double replacement reaction. So we're going to get NaNO3 plus CaOH2. And you can see the states that I'm giving my products. I determined those states by looking at my solubility chart to determine what they are. All right, so the next thing is balancing this. So I'm going to need 2 here and 2 there, and it's balanced. And so I start off with 4 grams of sodium hydroxide, and I want to find out theoretically what my mass of calcium hydroxide would be. I don't know what that is. All right, so now I'm going to get my theoretical yield by carrying out stoichiometry. That's step 1. Step 2 is to find moles. So I start with 4 grams and I use my molar mass of sodium hydroxide to find my moles. So I've done that step now. I've got my moles of sodium hydroxide. My next step is a mole ratio. And what I'm looking for goes at the top. So that is CaOH2. Goes up, oops, I forgot to write the moles. Okay, so this is going to be 1 mole of CaOH2 over 2 moles of NaOH. And so my moles of NaOH are gone, and I'm left with moles of CaOH2. And then, of course, the last step is to find the molar mass of calcium hydroxide. It's 74.10 grams per mole. And now what I can do is cross out my moles, and I'm left with grams. So I've solved my stoichiometry question, and this turns out to be 3.705 grams. Now, rounded to the correct number of significant digits, this is 3.71 grams. Now, the next part is the percent yield. And so what I'm going to do is substitute the numbers that I have from my question into the percent yield formula. So percent yield is actual over predicted times 100. And so this is going to be, and you can see from the question that the student, what they actually got in the lab was 3 grams. So that's going to be 3 grams over 3.705 grams and multiply that by 100. So when you do that, you will see that the value turns out to be 80.9716%. Rounded to 3 significant digits turns out to be 81.0%. Right? So not quite the 100 we expect for a high school lab, but it doesn't matter. It's still pretty good. And then it says, what reasons could there be why the yield was not 100%? And this is where, when we actually do a virtual lab of this, you will see where we lose some of this precipitate in the process. So a couple of reasons for this was maybe not mixing the reactants together. So not the full amount of products as we expected got achieved. So incomplete mixing of reactants. So we have an incomplete reaction. And then here's a really big one. And it's basically that we cannot, as much as we can, as we want to, we cannot collect all of the precipitate. So we are measuring reactants, putting them in a container together. Sometimes we don't mix well, or not all of the substance gets transferred, and then we can't collect all of the precipitate. So obtaining 100% yield is actually very hard to do and not expected, really, in a lab setup. All right, so I hope that kind of makes sense how to set it up. Again, it's always at what you actually got in the lab over what was predicted, so what you calculated as the yield should be, and then multiply that by 100 to get the percent yield. So question 2 then, it says, in another experiment, a solution containing 3.48 grams of copper 1 nitrate was mixed with a sodium chloride solution. A percent yield of 88% copper 1 chloride was obtained. What was the actual yield? So what did they actually get in the lab? We got a percent yield, but we don't know what the mass that they actually obtained in the lab was. So again, same process. We're going to have to find out what the theoretical yield was in order to find out the actual yield. So stoichiometry, balanced equation. So CuNO3 plus NaCl gives me CuCl solid plus NaNO3. And again, the states I obtained by looking at the solubility chart. I have 3.48 grams of copper 1 nitrate that was added, and then I need to figure out what the theoretical mass of precipitate that I would obtain from this reaction. So again, same thing. I have a balanced equation. My next step, as always, is to find moles. And my molar mass is 125.56 grams per mole. So that's done. And I have my moles of CuNO3. My next step, as always, is my mole ratio. I'm looking for CuCl, and I have CuNO3, And I'm well aware that that's a 1-to-1 ratio, but you are required to communicate your reasoning and that you know that that is a 1-to-1 ratio. So now I've converted it from moles of CuNO3 to moles of CuCl. And my last step then is going to use the molar mass of CuCl to figure out the mass of CuCl that I expect. And this turns out to be 2.74 grams. Now, for this one, I know the percent, so there's going to be, the way that most of you would probably solve it is just to substitute into your formula and work backwards. So this is actual over predicted times 100. So you would substitute in and you would put 88 equals your unknown over the predicted, which was 3.48 grams times 100, and then basically solve for x. But there's actually a much easier way of doing this, and that's basically using the percent for what it is, the percent of the whole that you got. So you know that the actual amount was 88% of the theoretical. So the other way that you could have solved this is changing your 88% to a decimal, 0.88, so divide it by 100, and then multiply it by your theoretical. You'll notice that whichever way you solve this, you're going to come up with the same answer. So what the student weighed out in the lab, what they obtained in terms of the precipitate they collected was 2.41 grams. All right, so that's the first calculation that we do. And it basically, what it does, what percent yield does, is it tells us how much from the expected amount we got. That's what percent yield means. Percent error or difference, and in fact, percent difference would probably be a better term, but we all use percent error in our description with this. And it wants to do, what it does is it lets us know how close to the expected result we were. So, how far were we off from the expected result? So it's not how much we got of the total, but how far off we were from the expected. So our formula here is the experimental, and I like to use the words, instead of actual, I like to use experimental because it seems like you know that it comes from the lab, over theoretical, which is where we get when we calculate it, divided by theoretical times 100. So we have to do an extra step where we subtract. Now, another thing that you will see is you see these lines here, and they really should extend all the way to the bottom, okay, because it goes top and bottom. And these are absolute value symbols. And if you haven't studied this in math yet, absolute value just looks at the number and not the sign. So this number is always going to be positive. Sometimes when you subtract these values, you're going to get a negative number, but you're going to ignore that negative sign and you're just going to report the positive of it. So report it as a positive number. So remember, percent error is always going to be a positive number. Those lines there indicate that you're just looking at the number and not the sign. So in high school reactions, again, we expect a percent error, if you were good in the lab, below 10%. So again, let's do some practice questions with this. And it says, a student obtained 5.8 liters of product from a reaction where the theoretical value was 5.9 liters. What was the percent error? So again, our percent error, you're going to see me writing it. So this is experimental minus theoretical over theoretical times 100. And again, you can see that I've included those absolute value signs. So we put in our numbers, 5.8 liters minus 5.9 liters over 5.9 liters, okay, times 100, and this turns out to be 1.7%. All right. Now, I can let you know that when we use these formulas in the lab, the one that we tend to focus on more is percent error. So we're more interested how close were you to the expected value, more so than how much of the product you collected. All right, one lasting question with this. And so it says it should be 143 grams. There should be no "the" in there. 143 grams of iron 3 oxide is combined with carbon monoxide gas to produce iron and carbon dioxide gas. If 98 grams of iron are obtained from the reaction, calculate the percent error. So again, we are going to have to calculate our theoretical value of this, okay, our theoretical yield. So we need a balanced equation. So Fe2O3, and it's combined with carbon monoxide, and it produces iron and carbon dioxide gas. I need to balance this out. So this is a 3 here, a 2 here, and a 3 here. Now, I've started with 143 grams of iron 3 oxide, and I want to find out how much iron we produced theoretically. So, as usual, have my balanced equation. Next step is to find moles. So 143 grams, and then I need to use the molar mass. There it is, and that helps me find the moles of Fe2O3, my mole ratio, what I'm looking for on the top. So the iron over the iron 3 oxide, and that now gives me the moles of the iron, and then I need to find and use the molar mass of the iron to find my theoretical value. And this turns out to be 100 grams. So now I can substitute it into my percent error equation. So it's going to be, now again in the lab, 98 grams were obtained. So my experimental was 98 grams minus my theoretical 100 over 100 grams times 100. And this turns out to be a 2% error or 2% difference. Okay, so that is how to calculate percent error and percent yield. You will see that they're actually related. So you can get one from the other by subtracting from 100. But even so, we don't usually calculate it this way. And again, percent yield lets us know how much of what we expect we actually got. Percent difference or percent error lets us know or see how far away from the expected result we got. So after this, a little bit of practice as always to make sure that you understand the concept.